So, welcome back. We will now start formally the theory of semigroups. Again, this topic is again maybe new to many of you. So, you have to really understand the new concepts and work out the full details. So, all the details again cannot be given. So, let me begin with a formal definition of what a semigroup is. Okay, so let X be a Banach space. So, I am not going to say that whether it is real or complex. So, it can be either one, Banach space. So, I denote by Bx the space of all linear bounded operators from X into itself. So, a family T non-negative real number contained in Bx. So, each one of them is a linear continuous operator from X into itself is called a semi group. So, in textbooks you actually see this expanded version. So, one parameter strongly continuous semi group. So, we just abbreviate strongly continuous or even C0 the semi group. Okay. So, every time we will not write that. So, this one parameter refers to this T non-negative. Okay. So, in the end I will make a remark on multi-parameter. So, that means T is also either in Rn or Rn plus. Okay. So, I will make a comment on that. If so, there are essentially two conditions. So, I will just write two conditions. So, T of T1 plus T2 T1 T2 for all T1 T2 non-negative. So, I will include here itself this T0 is identity. Okay. The second condition, this is the strong continuity. So, this is called semi group property. And then the strong continuity, actually strong continuity only at the origin at t equal to 0. Okay. So, this limit. So, in some textbook you also see there is a letter S is added, but we do not need that. So, just TTX minus X. So, this is the norm in the Banach space X as t tends to 0 is 0 for all X in X. Okay. So, this is different from the uniform converge. So, this we say that TT converges to the identity in the strong topology, not uniform topology. Okay. So, if TT is defined for all T for all Tt is defined. Tt is defined for all t in R of course satisfying the semi-group property and strong continuity. We say that Tt is a group. So, in this case, so we have when Tt is a group, so we see that T of minus T, so they are all invertible operators. Okay. So, everyone in this family is an invertible operator. Okay. So, let me state a result. So, immediately. Okay. So, let Tt be a, so let me not, okay, let Tt be a semi group. Then there exists a constant bigger than or equal to 1 and omega a real number such that norm of Tt is less than or equal to m e to the omega t for all t greater than or equal to 0. And the second one, so in the definition we only assume that this family is continuous only at t equal to 0, and now the mapping t going to Ttx. So, this is from R plus 0 infinity. So, into x is continuous. Okay. So, I am not going to prove that, but just it is an immediate application of the first part follows from the uniform boundedness principle, and the second one follows from the first part. Okay. So, this is not very difficult. Okay. So, so I already see here in this estimate somewhat exponential nature of this semi group. Okay. So, the next important concept is of generator of Tt, generate. So, it is also called infinitesimal generator. Okay. So, I will not use that Tt. So, that is our next definition. Okay. So, for tau positive, put a tau equal to tau inverse T tau minus identity. So, again of course, this belongs to Bx. Okay. So, here is the definition. So, the infinitesimal generator. So, let me write once, because in textbooks this is what you see. A is defined by Ax is equal to limit A tau x at tau stands to 0 plus. Okay. For all those x, for which the limit exists, for which the limit exists. Of course, this limit is in the norm of x. Okay, so that you keep on verifying. Okay. So these are all elements in A tau x. They are all elements in, as tau varies. So they are elements in the Banach space x, and so this limit is also in the norm of x. Okay. So thus this domain of A. Okay. So this is domain of A, set of all x in x, such that this limit exists. So let me write. And A is defined, A of x is defined at this limit. Okay. At this stage, it is only clear that dA is a subspace of the Banach space x, and A is linear. That is very clear, because all these A taus are linear. So A is also linear. Certainly, the 0 vector is in dA, but apart from that, as of now, we do not know whether how large dA is. Okay, so that's our next result. Okay, that's so. Let me state that. So let me not write everything in the hypothesis. So this we are always when general discussion is there. So TT is a semi group and A is its generator. Okay. So 3 parts. So dA is a subspace. And A is linear. This is clear from the definition. Okay. If x belongs to dA, then this mapping T going to ATX, TTX is differentiable and d by dt of TTX is equal to TTAX, and this is also equal to A TTX. Okay, and third part, so the domain of the generator is quite large. Okay, so dA is dense in X and A is closed. A is closed. So A is a closed linear operator. Okay. Okay. Now just look at the second part. Okay. So, if we define u of t is equal to t t x, x is in dA, then u is actually differentiable and we have this. AU and u0 of course is x. So, you already see that the semi groups are useful in studying this what I call abstract Cauchy problem, ACP. So, this we will discuss little later also, abstract Cauchy problem. So, this Cauchy problem is stated in the Banach space. Okay. So, we have a solution for this given this semi group and that here is generator of that semi group. Okay. So, essentially we see that, so this ACP is always solvable whenever this A can generate a semi group. Okay. So, I will also define that what that means. Okay. A small digression here, I will just come back to this proofs. Okay. Small digression. So, even if I am not using all these concepts, but they are useful when you study the proofs in detail by looking into some textbooks. Okay. So, here, so we are using here continuity, differentiability. Okay. So, let me make a general comment. So, let A B be an interval. Okay. In R. So, what we are considering, and consider a mapping, consider f from A B to x. So, these are Banach valued functions defined on an interval. Okay. So, since this is a metric space, that is also a metric space. So, we can certainly talk of continuity. Okay. So, since in a Banach space we can introduce different topologies, but here I always use this norm topology. Okay. So, with respect to the norm topology, we can talk of continuity, and of course, we can also talk of differentiability between mappings between two Banach spaces, but that requires the notion of either Gatto derivative or Frechet derivative. Okay. But that goes into linear operators on the Banach spaces, but in this special case where the domain is an interval, so differentiability is also no problem. Okay. So, we can just okay. So, usual you take the difference quotients divided by h. This we can do because this is a scalar. Okay. So, this is an element in x, and if this converges to some element in x, then we say that f is differentiable at this point, and we denote this by f prime t. Okay. So, this is because of this one dimension nature. Okay. This we cannot do in higher dimensions. Okay. Then we have to go to either Gatto derivative or Frechet derivative. But in this case, so essentially using for uh, intervals in R, this is fine for us. Okay. And again we can also define the integral of a continuous function. So same Riemann upper sum, upper Riemann sums and lower Riemann sums uh, integral of f. Okay. So for the scalar case, wherever you use absolute value, that you replace by the norm. That is the only change you see. Okay. The same theory can be developed even for continuous functions with values in a Banach space. So in particular, so we can define this A f t dt. Okay. And of course this is an element in the Banach space. Okay. Absolutely no problem. Okay. So in particular we have, let me just state that. So norm of A to B f t dt is less than or equal to integral A to B norm of f t dt. And again this integral is defined as limit of some sums. So again, so if let me use a different. So f s is in Bx, okay, then s of this integral. So this is an element in x. Okay, so this is just integral A to B s of f t. This is by the continuity. So in fact we can just improve that. So if A is closed, so this A is not generator. Okay, just let me use different one. Okay. This is for if B is closed, and f t belongs to d b, and this integral f t also belongs to d b, then this b of integral a b f t dt is same as a to b so even just closeness is sufficient, provided the image of f is in the domain of B along with this integral, because this integral is limit. So in general it may not be in dB, so we are assuming that also in dB, and then you used this closed property to get this thing. Okay. So this of course I am just doing for continuous functions. So one can even define integrable class of such functions, and they are required when we consider the evolution equation in the weak formulation. But since we are doing via the semi group theory, this continuity and differentiability is sufficient for our purposes. Okay. So with this small digression, let me just quickly show you how the results of this theorem regarding the generator are proved. Okay. So, let me just consider that 2 and 3. So, not in full detail, but okay. Proof. Okay. So, this is for the generator. Okay. So, let x belongs to the domain of the generator A. So, what we have to show is the mapping T going to TTX is differentiable. So, you consider the difference quotient. Okay. So, T of T plus H minus T of, okay, let me put that x, TTX and T inverse. Okay. So, I am fixing T positive, and first you consider H positive. So, similarly you can consider H. So, this one using semi group property. So, you see that no, sorry, it is not T inverse, it is H inverse, that is the difference quotient. Okay. So, this is a T of T, H inverse T of H minus identity x. Okay. So, this is also equal to H inverse T H minus I T T x. This is just semi group property. Now, look at the middle term. Middle term, especially this one in the bracket. So, since x is in dA, we know that this converges to, so Tt, and Tt is continuous. Okay. And that shows that the limit exists in other two terms also, and that is what we immediately see, d by dt of Ttx Ttax, and that is equal to At. So, we also see that this A and Tt, they commute on the domain of A. Okay. So, similarly, if work out for H negative, but you have to keep, so the T minus H has to be T plus has to be positive. Okay. So, you have to take only small h and same computation. Okay. So, this proves 2, statement 2. Okay. So, the statement 3 regarding the density of the domain dA and closeness. Okay. So, just let me just, so you also if you integrate, so you get an important relation here. So, Ttx minus x, and if you see the proofs, because we are not going to do many proofs. So, these are repeatedly used. So, Ts Ax ds. So, remember x is in dA, otherwise this is not even defined. So, this just follows by integrating that relation from 0 to t. Okay. As far as the third statement is concerned that the density of dA is dense. Okay. So, consider this. So, let x belongs to x and consider this element 0 to t Ts s ds t positive. So, this is an element in x. Okay. And now you consider this a tau of 0 to t x ds. Okay. So, by the stated properties of the integral and interchange of continuous operators with integral and some manipulation of the this limits. So, you finally, so tau is positive. So, tau inverse 0 to tau Ts t minus I. So, this is an easy exercise. Okay. And now, because this is continuous function in the integrand, so by averaging, so that converges to T0 Tt minus Ix, which is simply Ttx minus x as tau tends to 0. So, according to the definition, that means this is in dA and its value A of that is given by this. Okay. Okay, to just see the density. So, further we see that 1 by t 0 to t Tsx ds converges to x again in Banach space x as t tends to 0. Okay. So, these elements are in dA and this is only a scalar factor. So, by linearity again these elements are in dA, they are in dA, okay, and they converge to x. So, for any x in x, so we can find a sequence of elements in dA that converge to x. Okay. So, that proves the density and the closeness you use. Let me just say that closeness. So, again you recall the definition. So, let action belongs to dA, action converges to some x and A action converges to y. So, what we have to show is x belongs to dA and Ax is equal to y. So, you just use this relation. So, that is what I wrote that here. Now, you since x n are in dA, so you just use that. Okay. So, we have T x n, sorry. Okay, just one line. I will just T x n minus x n is equal to 0 to t T s Axn ds, and by continuity of Tt and this convergence, so the left hand side converges to Tt x minus x, and the right hand side you convince yourself. Okay, so we can take interchange the limit and integral, and you do get 0 to t ts Axn converges to y, so I get y. Okay, you just convince yourself that. So in fact you can use the boundedness of this Ts and you do that. Okay, and now you divide by t, and let t goes to 0, and that proves that x is in dA and Ax equal to y. Okay. So let me stop here, and we will consider some examples in the next class. Thank you.